name is Kenneth, and as already mentioned, I'll be doing this presentation with Ola. So I'll begin with the background, and then I'll invite him to come take things up. So as part of this project, we've had sponsors from all these people. You have been a very good contributor to this particular work. We have Brax as well, and then we have Oxford amongst the others. Also, as part of this particular project, we've had Net Zero also playing a very significant role in funding this work. MyTax and then Nova Scotia Agriculture also contributing to this work. So sustainability of the production process of wild blueberry actually focuses on, I'll say, increasing productivity, protecting the environment, and then efficient energy utilization on the field. I threw in this particular picture just to give us an idea of the emissions that are actually occurring. And globally, we could see from the different prospects, from the different countries, different continents, the major producers of these. And when it comes to climate change, as we've all witnessed in the past season, what has been happening on the field, it's a very important environmental issue. And at the heart of it is what I would call it as the greenhouse effect of things that are actually occurring, influencing this. And so we could see the different players and the different contributors. And when you narrow it down into Canada, in 2022, when this assessment was done, we realized that agriculture actually plays a significant role, and it's the fifth largest source when it comes to the greenhouse gas emissions. That is just above that of the heavy industry and then the electricity. However, there is still something more that we can do to actually whittle down this effect. Now, when you look at the agricultural sector, we have two main players actually contributing significantly to this. And we have the crop production aspects, and then we have the animal production. However, for some time now, agriculture has seen an uplift of about 39%, almost 40% increase. And the bulk of this is actually coming from the crop production aspects. And in this crop production aspect, there are so many practices that we engage in that enhances this amount of emissions that are actually happening. And so we can talk about the application of the biosolids, the inorganic nitrogen fertilizers, which I'll say we actually use on our fields. The farm machinery, we can actually do away with them. Decomposition of crop residue on the field, loss of soil organic, among a host of other activities that are actually happening on the field. I know we have actually chalked some very good success in trying to eliminate some practices, in a way trying to reduce the energy consumption, and in a way also trying to reduce the amount of emissions being done as a respect of our production process. Now, when we look at the production process, we know we go from our pruning to the harvest, and along these various cycles, there are emission levels that actually occur on the field. And as I mentioned, some of our practices like the use of fertilizers, like the use of machinery, and all of this emit some amount of these gases, which cumulatively affect our climate as a whole. Now, these levels of emissions, we are trying to assess something that I'll come to in a later term called a life cycle, looking at the different cycle, looking at the different processes of the production system and how we can actually limit these amounts that are being emitted. So this work was actually done by my supervisor, Dr. David Percival, somewhere around 2005, 2007. So it's fairly about 20 years, approximately 20 years, but there is a need for us to take some steps back, look at what has been done, because this work actually focused on energy consumption and gas emission. However, we still want to take it up a bit further because out of this work, we could see that some practices have been set aside while we focus on some, all in the interest of trying to whittle down the amount of energy that is being consumed and the amount of gases that are being emitted. So now looking at our production cycle, We've tried to identify areas as part of this process in trying to see where we can actually improve these aspects. That is one, nutrient use efficiency of the plants. When we apply the fertilizers to the plant, we want to actually reduce the amounts that are being applied. We want to actually incorporate other approaches to make these use efficient for the plant. We also want to cut back on the amount of agrochemicals using some remote sensing techniques, which will be spoken about briefly, and also looking at the emissions as well. What can be done to actually whittle down these emissions, looking at our production practices. So these forms the bulk of the research. And so about a year ago, we started with this work where we looked at reducing greenhouse gas emissions and improving the carbon sequestration potential on wild blueberry fields. And so as part of our objectives, we're looking at three main objectives, and that is one, to use the remote sensing techniques to reduce the quantity of fertilizers used, which I've mentioned, to increase the efficiency of applied fertilizers and reduce greenhouse gas emissions. And to the third, to develop homegrown practices that enhance carbon accumulation, long-term storage, and probably sequestration on the field. And so at this point, I would humbly invite Dr. Ola to actually come deal with the first objective.
All right, thank you, Kenneth. Thank you for providing an insight into the direction at which we are looking at with respect to this project. We are actually looking at how we can improve the production system, as he has said. I'll talk about the first objective. We are trying to reduce the fertilizer usage on the blueberry field. And we are looking at it from different aspects. It's not only the fertilizer usage, we are actually looking at also how we can reduce the emission with respect to the amount of energy we are putting into the production system. And then we try to put against together two spraying systems, a tractor-based spraying system and a sprayer drone. We have this set up for our equipment that we used. For mapping the field, we use a kind of mapping drone, which is a DJI M300, which is a kind of enterprise system that can actually rapidly map a very large area. And to be able to manage our field, to map our field, we are using a high definition optical camera and also a multispectral camera that gives us an information about the health of the plants on the field, and a way by which we can do what we call image classification, which helps us identify the different patches of features that we have on a wild blueberry field. Also, we have the sprayer drone on our setup, which is the DJI Agras 340. There's a typo right there. Okay, this is also a very powerful sprayer drone, which can actually, help us in spraying our field if we don't actually want to go by using a tractor to spray. And here we have a simplified workflow of how we map our field and produce a result that can be used to spray the field with respect to, I'm talking about the prescription maps. We take the mapping drone DJI M300 to the field, we fly it over the field, we collect what we call overlapping area photographs. These were processed to what we call digital automosaic. And when we have automosaic, we can now proceed further in the realm of geographic information system to actually classify our fields. In our setup, the field were classified into bare surfaces, blueberry coverage, and weed patches. So when we have these three, we can now decide to create what we call prescription map from these three classifications and determine which amount of fertilizer is going to be applied onto these different patches. This information are actually encoded in the prescription map. And in our own case, what we do is that when the sprayer system is coming forward and it comes over a blueberry canopy, apply fertilizer. When you are going over bare surfaces and weed, don't apply fertilizer. And this prescription map is also applicable in weed management with respect to application of herbicides. And when we have the prescription map, this can be sent to whichever spraying system you are using. In our setup, we have a tractor-mounted system which has a 20-foot boom, and the same prescription map were also sent to the sprayer drone, and the two systems were compared with respect to amount of energy they used in spraying the field. We try to measure the amount of fuel usage with respect to both devices, both spraying system, and also we try to assess the efficiency of both systems in getting the spraying task done. And to go about this, we have to try our setup at Kemptown and then at Eltown with a dimension of 70 meters by 12.8 meters. And then we have five strips. We have the control. Then we have a blanket application and prescription application for the two kind of spraying system, which is the tractor mounted one and the sprayer drone. The first thing that jumps to you looking at this result is the time required for the system to complete this spraying. We realized that at all the measurements that we did, the drone gets to complete the spraying system far more quicker than the tractor-based system, and we have a completion time that is less than half of the tractor-based system at any time that we conduct this experiment. And we can see that there is really no significant difference between the prescription-based spraying and the blanket-based spraying, because in both cases, the sprayer system actually travels the same distance. It is only shutting off and on the nozzles when it gets to the different patches that are mapped and identified on the field. We also measured the amount of energy that was used. If you look at this data, we also realized that the tractor-based spraying system actually used much more energy than the drone. And the value of energy used by the drone is actually measured by the energy expended in recharging the battery in the field. If we had used a renewable energy to recharge this battery in the field, the tractor-based energy, the drone-based energy used might be approaching a value of 0. But in this case, this is what we measured on the field on our setup. So we have about 10.9, about 1.5 times 10 to the power minus 5 terajoules of energy, most cases trying to use to recharge the battery of the drone for each of the experimental setup. But the tractor-based system used much more energy. And looking at the amount of emissions that were measured, we see that the tractor-based system, in most cases, released about 35 kilograms per hectare of carbon dioxide, which is also much, much higher and significantly different from the one measured from the sprayer drone. Alongside this, we also try to measure the efficiency of the spraying system, okay? When we use the drone versus when we use the tractor-based system, is it effective in getting the plant up? And I must say that both field trial sets are actually in their sprout year, and we try to use normalized different vegetation index that is derived from the multispectral camera used to map the field to assess the health of the plant across the growing season. We realize that there is really no significant difference between the growth, and the trend of growth actually follows the normal trend, peaking, vegetative activities peaking around June, July. In the second field, we also experienced a similar trend, but the trend a little bit deviated from normal because we experienced a kind of rust disease in the second field. Alongside that, we also use a water testing paper to assess the spray distribution and the penetration of both spraying system. And the result shows that the drone actually provide a better distribution and penetration of the agrochemicals that is actually being sprayed. At the top canopy, the drone achieved a 56% sprayed area as against this 26% achieved by the tractor. And then we can see that at the bottom canopy, we still have a far higher penetration from the tractor as against what the drone, from the drone, I mean, as against what the tractor can achieve. And this is partly due to the action of the drone. It has a powerful propeller that creates a kind of a downwash that pushes the agrochemical that is being sprayed further into the plant structure. Also, there is a little bit of agitation of the plant system when it is being sprayed, really helping in pushing what is being sprayed down into the system furthermore. And also, there is also a kind of an improvement with respect to the kind of nozzle that the drone uses. That's a kind of atomizer that actually helps you to control the size of the mist that is being produced from the spraying nozzles. And we see that generally the sprayer drone actually completes the work a little bit more faster, uses less energy, and it has also what a very low emission with respect to the greenhouse gas that were measured in this experiment. And some of the additional advantages that there is a kind of intense distribution of the agrochemical that is sprayed, helping in having an effective spraying operation. And it's a hovercraft, therefore there are no tram lines, so it could result into less damage onto the crop. But there are a few drawbacks. In our experiment, we actually spray with the drone at an altitude of 1.5 meters, which is the minimum achievable. At this rate, it is also possible for you to fly higher than that, but this flying altitude actually makes the system susceptible to drifting because you are flying at higher altitude. Also, the drone itself is unable to support a prescription map that has a small spatial resolution. You might actually need a wide patches of area that differentiate from one place or the other with respect to talking about the lowest area that can form a minimum management zone with respect to what the drone can actually manage. And then currently it cannot be used for pest control product because it has not been permitted to spray pest control product with a drone in Canada as of today. Although there are some testing on the way, and we are hoping that a regulation will be produced or released very soon that will allow us to be able to use the drone to apply pest control products on our blueberry field. So with this simple comparison, we realize that well, the drone has a lot of advantages with respect to using it to control or to do spraying operation on a wide blueberry field. But some of these drawbacks might have to be worked around before, let's say, going forward. Okay, I'll invite Kenneth to actually talk about some other aspect of the experiment. Okay.
Thank you. He's not done. He'll be back to answer questions if there are any. Yeah. So moving on to the second objective. In this objective, we try to efficiently utilize fertilizers using nitrogen-fixing bacteria and then inhibitors. So as has already been said from the onset, we're trying to see how best we can reduce the amount of fertilizers by incorporating these nitrogen-fixing bacteria and then also some soil microbes. So the two main points in this objective was to assess the impact of the biological enzyme on greenhouse gas emissions, and then assessing the impact of these enzymes on the physiological and then morphological aspects of the plant. And this particular research actually began one of it from two sites last year, where we had some trials set up in Merseyside and then also in Mount Tom. So in this trial, we tried to use this biological organism, which is Envita. I'll say a manufacturer product name, the Envita, bearing the organism. And then I also use the urease and then the nitrification inhibitors, where they try to slow the amount of, I'll say, hydrolysis of ammonia. And then like those two organisms, which are also used. So in terms of assessments, I assessed the greenhouse gas, which is a different aspect as well, the leaf nitrogen content, the leaf area index, flora and vegetative buds. With the greenhouse gas emission work, we actually started it this year in June, which we actually measured the collection over a 12-day period. And in trying to assess that work, we use this particular treatment. We use this particular treatment where we have our control with our liquid fertilizer being alpine. So we did a combination of the alpine and then some microbes, which is the urease inhibitor, where we had our alpine with our nitrification inhibitor, where we had the alpine plus all the two inhibitors, and then we had our granular fertilizer as well. So with this work, which I mentioned, that was began last year, and then I finished it up this August. So we tested the nitrogen fixing organism, which is the Envita product. So with this, I was looking at the floral bud numbers, and the floral bud numbers are the mericidin side, and then also at the Mountain locations. We realized that there was some kind of a slight advantage in trying to use this biological fixing organism. We could see when we are looking at the floral bud numbers, we had some significant effects with our treatments as compared to the no Envisa treatments. And today it looks like we've had a lot of teachings with these letters where there are differences. You realize that there are significant differences where the letters are different. But when they are the same, probably there are no differences. So we could see those differences at the mericidin side, and the same also applies with the floral buds. We could see some more higher counts under the nitrogen fixing bacteria effects with the no effects. Now, when it came to the berry yield, we realized that there was a challenge with the Mountain side. And today it looks like a lot has been spoken about the pollination effects. And then with the red chip soil, we actually saw a lot of it on the field, which really affected the yield. So we could see very low yields, irrespective. But when we look at the mericidin side, we realize that the effects of probably the Envisa products was much more significant when we look at the lower rates of the fertilizer application. So we realize that with our treatment two, that is the 20 kilogram of nitrogen and the 40 kilogram of nitrogen, we really had very good yield effects in that aspect. So in short, we were trying to make the point that trying to add up trying to combine those nitrogen fixing bacteria with lower yields, we seem to see some very good improvements in terms of the yields that we were obtaining. Now, when we come to the greenhouse gas effects, as I mentioned, it's actually a build-up from some work which was actually done in 2026, which actually focused on ammonia emissions. But with this one, we're trying to look at the nitrous oxides and other chemicals as well. But in this emission, we realized that, and what I did in this analysis was to use the control as a base to find the differences between the different treatments as well, which were applied. And so in this, we realized that there was some kinds of emissions in all of the treatments. However, we could see some very high emissions when you look at the alpine plus urease combinations. However, I would want to state that this particular analysis is still ongoing because we're actually collecting data from two sides, but I'm just representing data from just one side. Now, when we look at the cumulative assessments over that 12-day period, we realize that this particular treatment, which is the alpine plus the urease inhibitor, was actually giving us very low emissions. And I was just trying to do a comparison between what was done on the high bush blueberry field in comparison to what has been done or what I did with the low bush. And I realized that there is significant differences because of the amounts which are actually being emitted on the high bush, which I haven't actually put on the slide. As I mentioned, this analysis is ongoing, but probably at our next meeting or at our next presentation event, probably some of these records will be updated. So in summary, with this particular objective 2, it generally appears that the nitrogen-fixing bacteria, which is the Envita product, had an advantage over the non-treated in the growth parameters that we examined. I listed a number of parameters that I examined: leaf area index, floral buds, the plant density, but I only talked about the floral buds and then the yield. So we could see some level of advantage of the nitrogen-fixing bacteria as compared to the non-ones. The study demonstrates that combining the organism with reduced N fertilizer enhanced yield, and we saw in the graph or in the table, which actually showed to us. The study also demonstrates the marginal effects of the urease inhibitor in emitting low greenhouse gas compared, which are also highlighted in that table that we saw. And there is also an interesting thing when I was looking at my results. I saw some decrease in some amounts of I'll say these emissions, and reading around, I realized that the wild blueberry field actually hosts a lot of microbes, a lot of soil organisms, and these soil organisms actually, in a way, feed on some of these gases, which is a very positive thing, because even though there are emissions, but we still have these soil microbes that are more or less feeding on these gases, more or less reducing those amounts on the field. It's something very significant, which I actually want to give it a more read, just for better clarity. Now, with the third objective, that is trying to look at the carbon sequestration and the carbon accumulation of the production system as a whole. So we try to assess the carbon accumulation potential of the wild blueberry field. And in this objective, we actually had 2 sites, one in Kemptown and then one in Adamsfield. And then we also looked at the bed as a way of trying to look at both the sprout field and then the crop field, because the idea is to try to have a holistic cycle, trying to understand the carbon potential of the whole cycle of the plant. So we had some sprout fields and then some crop fields. And with those treatments, we try to actually have a control, and then we try to, I'll say, have a blanket application of fertilizers, and then we had alpine plus the biological enzyme, which is the Envita, and then we had a prescription mark application also as a treatment. And then in trying to measure some of our parameters, we try to look at the shoots and the root dry weights of these particular treatments as an attempt of assessing their carbon content. And then also we try to look at the CO2 emissions from these particular treatments. So in the process, we have this tube. So we took data from every treatment from the soil. We take off the plants around that area. So with this pipe, we just insert it into the ground. So we harvest the plant, the shoots, and then we have the roots as well. So we go down about 15 centimeters into the ground. Then we can actually assess the roots of this from the soil. And so we try to test the carbon contents of the soil, the carbon contents of the root, and the carbon contents of the shoot. And with this, it gives us a very holistic idea of that potential of the plant. And in addition, we also have this device that we use, that's the CO2 flux measurement, that tries to measure the amount of CO2 which is either being emitted or being absorbed from the atmosphere. And that's the device that we have on the screen here. Very interesting device, which I'll show some results up very soon. So when we do this dry weight analysis of the 4 different treatments that we actually observed, which I showed earlier on, you realize that there is something interesting happening when we combine alpine plus the nitrogen-fixing bacteria. In both scenarios, we realize that the shoot dry weight, there is an increase in the shoot dry weight, and then in the root dry weight for the alpine plus the Envita treatments, and which is something quite interesting. As I mentioned, we are still ongoing. We're trying to analyze this data, but this is what we are seeing so far with the data we've actually collected for these different months up to September. And it's interesting also trying to look at looking at the sprout here and then looking at the crop here. You realize that there is a bit more of dry weight being accumulated in the crop here as compared to the sprout here. And the amount of dry weight is more or less giving us an idea of the amount of carbon that the field can actually sequester or accumulate on the field. And then also when we try to look at the CO2 assessments, you realize that, so what we did in the earlier picture that I showed you, we had this device with a pot where we go to measure the CO2 from the plants. And so we measure from the plants, and then afterwards we take off the plants, and then we still keep the chamber on the soil, and then it takes that reading. So the measurements with the plants on top gives us this blue area. And then when we take off the plants, we do that measurement, and that is with the orange aspect. So all that this is telling us is that there is a lot more uptake when the plants are there or present on the field. There is a lot more uptake. But when the plants are not there, we have some amount of emissions. Over here, we have these amount of CO2, which is being emitted, and that is as a result of like the soil respiration and the organic matter decomposition on the field. So in a nutshell, it is just trying to tell us that when the plants are there, these emissions more or less looks non-significant because the canopy is more or less trying to absorb every kind of CO2 that seems to be produced on the field. And so the other aspects that has to be done is also trying to understand the soil components, the soil carbons from the soil, which we are yet to actually determine. So in general, trying to combine all that I have said concerning this third objective is that generally it appears that the alpine plus the Envita treatments enhanced shoot and root biomass accumulation. As I explained, the dry weight actually tells you that there is some more accumulation, those weights. And dry matter weight quantifies the stored carbon. So plants take up carbon dioxide during photosynthesis and convert them into biomass. So if we measure these biomass, it's more or less an idea of these accumulations that are happening. Overall, what this particular research is trying to tell us is that the study demonstrates the potential that the wild blueberry field is a strong sink for carbon sequestration and accumulation. So I mentioned something about life cycle analysis. And the life cycle analysis is trying to look at the whole cycle of the production system and trying to see how viable this system is in terms of sustainability, in trying to reduce the amounts of emissions, in trying to sequester carbons, in trying to accumulate more. And this more or less has the potential in trying to earn us these carbon credits, which we have seen governments and the federal systems actually try to initiate some of these processes. So in a nutshell, that is like what this project is targeted towards. I know Peter's actually mentioned about this yesterday, that Dave is doing something complex, and there's the complexity trying to be break down in simple terms for us to understand. Yeah. So thank you very much. And that is so far the findings that we have for now. If there are any questions?
Is there any questions?
The payload of the T40 is actually 40 liters. It can take 40 liters of liquid when you are spraying. Also, something about that weight when you are spreading some solid fertilizer. Okay, so the idea is trying to compare the two systems that we used. We have a 500 liter capacity on the tractor, and we have 40 liters on the drone. Okay, so the drone completes it faster. The drone has the capability to optimize refilling the tank. And if we look at the two systems, even if we have a full load of 50 liters on the tractor, and we have a refilling of 40 liters on the drone. The setup time, refilling time, will not actually make that time longer for the drone, because you can actually refill quickly and you send it back to continue the task. In our comparison, the drone will still nearly get the task done faster than the tractor-based system, because we can actually optimize the refilling, even battery replacement when we are out there in the field. But one might ask, we only did the experiment with a 20 feet long boom. What if we have 80? Okay. The tractor, the drone also has a kind of configuration, because with respect to our trial, we try to match the configuration of the tractor with what the drone can do. If we tweak the configuration of the drone, it can still match the performance of high performance tractor system, even if it has 80 feet long boom from our experiment so far. You're welcome.
Great. Thanks very much. We're looking forward to this as this project develops. Well, I want to thank everybody for staying for the 2 days. I think we had a lot of good discussion, and like I said, stay tuned for announcements on our winter meeting that we'll be having in early April in Moncton, and wish everybody a safe journey home.